In this lesson, we are going to model data with exponential functions and model data with power functions. In the first example, we're going to learn how to write an exponential function in the form y equals a times b to the x, whose graph passes through two given points. So the first step is to use our points and make two equations with the values that we're given. So if our function is y equals ab to the x, we get 0.0625 is equal to a times b to the negative 1 from our first point. Our second point will give us 32 equals a times b squared. Our next step is to solve one of our equations for a. It does not matter which one you choose. I'm going to pick the first one because I'm noticing that it's going to be rather easy. So we get 0.0625 is equal to a over b, because we know that if we have b to the negative 1 power, it's just going to bump down to the denominator. And if we solve for a, we multiply both sides times b, so we're left with a equals 0.0625 times b. Our next step is to use this new a value and plug it into our second equation. So now we have 32 equals a, which is 0.0625b times b squared. We can rewrite this and simplify a little because we know that if we're multiplying, we can combine those b's to get b cubed. Now we're trying to solve for b, so we're going to divide by 0.0625. We're going to get 512 is equal to b cubed. Taking the cubed root of each side, we'll be left with b equals 8. So then our next step is to take this b value, plug it back into our a equation so that we can find out what a is. So now we have a equals 0.0625 times 8. So our a value equals 0.5. And now we have found what our a equals, we have found what our b equals, so we're ready to make our exponential function. So we have y is equal to a, which is 0.5, times b, which is 8, to the x power. And that's our exponential function. The next example is going to be modeling our new exponentials, and the problem says the ordered pairs down here represent the number of years t buying a car and its trade-in value v in dollars. So our ordered pairs give us t in years, v in dollars. The question is to draw a scatter plot of the ln of v versus t. And so what we're going to have to do here, first I'm going to label my graph, the ln of v on my y-axis and t on my x-axis. We are only given the v values, so we're going to have to do a little bit of computation before we can start plotting our points. The ln of v, we'll do our first point, would be the ln of 12,995, which is going to give us about 9.6. And then if we take the ln of our second y, which is 9,050, we'll get about 9.1. And if you'd like to, you can plug the rest of these into your calculator. If not, I've already done so for you, so you can just trust my graph. So what we're going to do first is start plotting. We have 0, 4, 8, okay, so our first point is 0, ln of v, which is 9.6. So that'll be up here. The next point is 1 ln of 9,050, which is 9.1. And for the rest of them, we're going to have 2, and I think it was about 8.8. 3 is about 8.2 or 3. 4 is right on the dot there, 4 at 8. 5 was just under 8. 6 is just over 7. 7 is right on the dot, 7. And 8 is just under 7. So the question is an exponential model a good fit for the data? And the answer is yes. Why? Because our model gives us a linear graph. Not necessarily that all of our points lie right on the graph, but they're not scattered all over, so there's no correlation whatsoever. So the answer is yes, because we have a linear model. The next question is, find an exponential model for the original data. Going back up to the original amount, ignoring the ln's now, it wants us to do what we did in the previous example and find an exponential model. So we know the first thing that we have to do is pick 2 points. We have several here to pick from, so I am going to pick 1, 9,050, and 6, 1,550. From there, we know that we have to plug these values into our equation, which is y equals ab to the x, and again, y equals ab to the 6, which is x. Okay, next, solve for a. So I'm going to choose this one because our b is by itself. So we get a equals 9,050 divided by b. Plug that in to this equation, which will give us 1,550 is equal to 9,050 over b times b to the 6th. Our b's here will cancel down to b to the 5th because we're dividing. We can combine those terms. So then we will get b to the 5th if we divide by 9,050 is going to be about 0.171, taking the 5th root of both sides. We will get b is equal to about 0.703. And plug that back into our a equation. We will get a is equal to about 12,880. Okay, so we have our a value, we have our b value. They want the exponential model, so we plug it in. Y equals 12,880 times b, which is 0.703 to the x power. And that is our exponential model. Okay, so this next example is going to be a little bit trickier, but I know we'll be fine. We want to write a power function now in the form of y equals a times x to the b power whose graph passes through 2 given points. So the first thing we do, just like before, is plug in our x and y values into our 2 equations. So we have 8 equals a times 3 to the b power, and we have 12 equals a times 9 to the b power. Once again, first thing we want to do, solve one of our equations for a, and I believe I'm going to do this one. So we get a equals 8 over 3 to the b power. Plug that in to our other equation. We get 12 equals 8 over 3 to the b power times 9 to the b power. We can simplify this to get 12 equals 8 times 3 to the b power. Because we know that since these have the same base, we can, or the same exponent, we can combine them. 9 divided by 3 is 3. Divide both sides by 8. We get 3 to the b power is approximately 1.5. Okay, and how do we get rid of this 3 to the b? If you remember correctly, we are going to take the log base 3 of both sides to bring that b down from the exponent. So what we have here is just b equals log base 3 of 1.5. Again, using our change of base, we can find that equals log base 10 of 1.5 divided by log of 3, which will give us approximately 0.37. And that, again, is our b value. So now that we have our b value, we can plug that into our equation up here. And that will give us that our a value is equal to about 5.33 after you've computed everything. So we have our a value, we have our b value. Writing our power function, we will get y equals 5.33 times x to the 0.37 power. And that's our power function. Once again, quite a few steps, but remember, all we have to worry about is finding our a and b values and plugging them back into our equation. So once again, what we're going to do is we're going to model, but now it's going to be for our power model. So the problem is the ordered pairs TR describe the circular area R in square feet that oil from a leaking oil tanker covers T minutes after it begins leaking. So again, we have T and R for our X and Y values. The question is, draw a scatter plot of the ln of T versus the ln of R. So this time we have to take the ln of both of our coordinates before graphing. Once again, I'm going to do one point. I know that you know how to plug in this value into your calculator, and if you need a little reminder, there's a button that says LN. Push that, push the number, and hit enter. So we'll do the first point. ln of 1 equals 0. And ln of 28.26 equals 3.34. So what we're going to do is plot all of these points into our graph. If we want to label, we have 0, 2, 4, 6, and 8. 2, 4, 6, and 8. Okay, so plotting our first point, again we have 0 and 3.34 to about there. And then if we do our second point, we have 1.16 and 6.6, which is right about up here. The next point is going to be a little bit after the 2, but way up above the 8. And we have the next 3 points in that same area. And if we plot 4, it's going to be close to 10. So the question again is, do we have a power model that's a good fit for the original data? And again, the answer is yes, because our graph is still rather linear. Once again, some of the points don't lie directly on it or close to it, but they're not over here at, 6 and 2, or up over here where we're not even sure. They're all in the same area in a linear fashion. So the answer here is yes. The next question is to find a power model for the original data. So just like the prior example, what we're going to do is pick 2 of these coordinates and plug them into our equation. So I'm going to choose 1 and 28.26 and 10 and 2,826. Okay, once again, the first thing we want to do is plug those values into our equation. So we get y equals 2826 is equal to a times 10 to the b power. And then we have 28.26 is equal to a times 1 to the b power. We know that 1 to the any power is simply itself 1. So we get a equals 28.26. And if we plug that in, we get 2,826 equals 28.26 times 10 to the b power. Simplifying this, we get 100 equals 10 to the b power, and we know that 10 squared is 100, so b equals 2. We have our 2 values here. B is 2, A is 28.26. So our equation we get is R equals 28.26 times T squared. And that is our power model. Okay, and last thing we're going to do is just a quick review. When we're solving our exponential and power functions, remember the first thing we want to do is substitute the coordinates in. The next thing to do is to solve for a in the first equation, and then substitute that a into the second equation to give us b. After we know b, solve for a, and after we have both our a and b, we plug those into the original equation. And remember, when finding a model, if the points in the scatter plot lie close to a line or similar to a linear fashion, an exponential or power model should be a good fit for that original data. And that will be the end of the lesson.